Welcome to a lesson with Dr. Powell. Let's take a look at a derivation for a formula of the discriminant of a power basis for a number field, k, as an extension of q. Okay, so we're going to let f be the minimum polynomial of alpha, where we're taking powers of alpha. If we take f of x and divide out by x minus alpha, let's think of f of x as being a as its Taylor series centered at alpha. So what's not written here are higher powers of x minus alpha. You plug alpha into, well, and then algebraically, those cancel with x minus alpha to get you still x minus alpha. You've plugged in alpha, it's just 0 out there. Now here, in this part, taking a limit, you can cancel out here and plug in alpha and just get f prime of alpha. So if we could think of the limit of this thing as x heads to alpha is actually f prime of alpha. Now through some cancellation, we still have the same limit, which means via in some cancellation, we will still have this being exactly equal to f prime of alpha as follows. We can let f of x be equal to the product of distinct factors, x minus phi of alpha, where phi ranges through the endomorphisms of k into c, into the complex numbers. And then if you divide out by x minus alpha, you're just dividing out by one of these factors, namely when phi is just the identity. So if we just take this product, we have no domain issue anymore, and we could simply plug in alpha. When we plug in alpha, we end up getting this is equal to f prime of alpha right here. Now, let's see what happens when we take the norm of f prime of alpha. So from k down to q, well, we basically take a product over different endomorphisms of k into the complex numbers of that product that we just found, that we just had. So this product, we take tau of that product, and tau will come in here to the alpha and phi of alpha. And through some rearranging and relabeling, thinking of phi I, so labeling the different endomorphisms as phi I, so letting tau be kind of like phi I and phi being like phi j, where phi 1 might be the identity. So we kind of relabel this product in this way, and then we can say phi I minus phi j is equal to some phi L. Okay, so just let L be whatever I times j might be, and then you could write it out, and then you can relabel. You can relabel L, or j going from 2 to n is the same thing as L going from 1 to n, except it will never be equal to what I is. So we can do that. We have this product, which we can now write out this way, since we have I and j and I and L, one being bigger than the other, smaller than the other in both ways. But if we just take one of them, then we can write out both in the following way. So this is one way of rewriting it. And then if we factor out a -1 from one of these guys, in fact, there's exactly n choose 2 -1s to factor out, so -1 to the n choose 2, then we can put a square on this. And if you notice, this product right here is actually actually equal to the square of a Vandermonde determinant, which is equal to the determinant of a trace form, which is the discriminant itself. So this right here, if we assume that this product is the discriminant, then we're basically done. We can take this discriminant, we can multiply this -1 and the n choose 2 to the other side. So we just multiply it to the norm here, and the discriminant's equal to that times the norm. So this is another formula for computing the discriminant. Thanks for watching.